Section 4.6, diagonalizable matrices. Let's jump right into it. Definition. Matrix A, n by n matrix, that means square matrix, is said to be diagonalizable if it is similar to a diagonal matrix, which means that there exists an invertible matrix U, which is also of size n by n, and a diagonal matrix D, which is also n by n, such that the A matrix equals to U times D times U inverse. And the reason why we like diagonalizable matrices, first of all, diagonal matrices, because their eigenvalues are the diagonal entries. Also, the powers of the matrix is just the powers of the diagonal entries. If you think about how we multiply them, inverses of diagonal matrices are also diagonal matrices with their reciprocal of the original diagonal entries in the diagonal entries. And for example, solution to an associated linear system is just the right-hand side vector divided by the diagonal entries entry by entry. And there are many other nice properties. So we like diagonal matrices, and then we wish to make other matrices also diagonal with this similarity transformation. The main theorem is this diagonalizability theorem that says that if we have a n by n matrix A with complex entries, and suppose that A has exactly k distinct eigenvalues, lambda 1 through lambda k, these are also complex numbers, then the sum of the null spaces of A minus lambda 1 in plus null space of A minus lambda k in is a direct sum. Moreover, the following statements are equivalent. A is diagonalizable. The dimension of the null spaces of A minus lambda 1n through the null space of A minus lambda k in equals to n. So the dimensions of these null spaces add up to n. And the sum of the null spaces is a direct sum and equals to the whole Cn vector space. So to prove this, first we go from 1 to 2. Suppose that A is diagonalizable. Then from the formula A equals to U D U inverse, we have that A minus lambda in equals to U D U inverse minus lambda in. And then we can write this I as UI U inverse. And once we have this difference, we can move the lambda to the right-hand side of U, since it's a scalar. And then we can factor out U on the left and U inverse on the right. So we have that A minus lambda in equals to U times D minus lambda in U inverse, which means A minus lambda in is similar to D minus lambda in for all lambda complex number. Then we know that similar matrices have the same null space because the U and U inverse parts have no contribution to the null space, since if U is invertible, that means its null space is only the 0, and the 0 is always there in the null space anyway. And that means then that the dimension of the null space of A minus lambda in is equal to the dimension of the null space of D minus lambda in for every point lambda in the complex plane C. In particular, if lambda is an eigenvalue like lambda j of the matrix A, then this dimension of the null space of A minus lambda j in is actually gamma j, the geometric multiplicity of the eigenvalue. So what we have is then that this equals to the dimension of the null space of D minus lambda j in. And this equals to the number of times the number lambda j is repeated in the diagonal matrix D. Since that's how we got the diagonal matrix lambda, or D, before. This also means then that gamma 1 plus all these gammas up to gamma k equals to n. Since altogether the diagonal entries add up to n, since D is an n by n matrix, and we have that 1 implies 2. See that 2 implies 1. We set gammas to be the null spaces, the dimension of the null spaces of A minus lambda j I n, the geometric multiplicities, and then we choose gamma j linearly independent vectors u1, u gamma j from this null space, not the dimension, but the null space. So the basis vectors basically from the null spaces. Then the vectors are n vectors, so we can put together these vectors into a bigger matrix uj, and this uj matrix is an n by gamma j, since we have n entries, n rows from the components of the u's, and we have gamma of j of them. We also have, if you multiply this uj matrix from the left with A, writing out that this U matrix is just the column vectors from the basis of the null space of A minus lambda j I n. So we can multiply this U matrix column by column with the A matrix from the left. And then because these are bases of the null space, we have that A times U vector is just lambda j times the U vector, since that basically the definition of these vectors, that these are the eigenvectors corresponding to eigenvalue lambda j. So we can replace AU with lambda j u's in these columns, and then since lambda j is just a scalar factor, we can factor it out on the right hand side. It's a scalar, so it doesn't matter which side you are multiplying these vectors. The multiplication is entry by entry anyway. And then this multiplication can be written as uj lambda j with capital lambda, where capital lambda j is a diagonal matrix of size gamma j times gamma j with lambda j in the diagonal. So for this you have to think about how we multiply with a scalar, that you multiply each entry, and how you multiply a diagonal matrix with another matrix on the right hand side, or this is U is on the left hand side. So then we have this AUJ equals UJ lambda j, and we can combine these into a larger matrix by writing U equals to U1 UK, collecting together all these matrices and collecting together the lambda j matrices into D diagonal matrix by putting the lambdas together into the diagonals. Then we get, and it's important to understand the structure of these block matrices and the sizes and how we multiply them. So we have then this big U matrix, big row vector of the U matrices, and then this D diagonal matrix is the diagonal matrices, matrix of the diagonal matrix, so lambdas put together. These are each diagonal matrices, so these are block. This is a block matrix with 0 entry of diagonal. And then, because D is diagonal, what we have is when you multiply basically like a row vector and then the columns, we get U1 lambda 1, then and so on. At the last column, when it's multiplied with this row, only this lambda k is picked up, so we get uk lambda k. And then, because the lambda j's are diagonal, multiplying, and they have actually just the same lambda eigenvalue in the diagonals, that means that we can replace this diagonal matrix multiplication with just multiplication with lambda 1 complex eigenvalue. And then it doesn't matter which way you write, you can write it on the left hand side as well, since this is now scalar multiplication, or a multiplication with a scalar. And then what we have is what we had before, that this equals to the AU1, AUK matrices, and then A can be factored out on the left hand side. And what we get is these U1, UK matrices are giving us the big U matrix. That means that looking back where we started, what we have is that A times U equals to U times D with these big matrices. And since the eigenvectors corresponding to different eigenvalues are linearly independent, that was a theorem before on the number of eigenvalues, the vectors in U are linearly independent. So first of all, they are linearly independent in the indexed U's because they are put together from the eigenvectors of the corresponding to the eigenvalues. So basis of the eigenspace. And then in between these different U's, we have independent vectors because they correspond to different eigenvalues. So that means the vectors in U are linearly independent. We also have that the sum of these gammas, gamma 1 through gamma k, equals to n. And that means that U matrix has a full rank, and hence it's invertible, so that we can write from this identity, we can write that A equals to UD U inverse, which means that A is diagonalizable. So we have from 2 to 1 also. To prove from 2 to 3, implication that if we know that the dimension of the null spaces summed up equals to n, then the direct sum of the null spaces equals to Cn. Since the dimensions summed up, we do have that the sum equals to Cn, because Cn is the only space with dimension n here. The subspace cannot have less n's or the same number of n's, and then we cannot go outside C because we are working with complex vectors. So we definitely have that the sum equals to Cn. What the point is here now that we actually have the direct sum. So for this we use again this theorem about the number of eigenvalues that says that since the vectors corresponding to the same eigenvalue are independent because we are using the null space basis elements, and because the eigenvectors between the different null spaces are linearly independent, then what we have is that the null spaces of A minus lambda j in sets are altogether k linearly independent from each other. And then the lemma about the direct sum that we considered last time says that if we have a sum of finite dimensional subspaces where every set of vectors u1, uk with these u's from the separate subspaces is a linearly independent set, then then and only then we have a direct sum. So this is now satisfied. We have linearly independent vectors, And that means that we have a direct sum, which implies 3. And then 3 implies 2 because the definition of the direct sum implies that the dimension sums up to n. That was actually the part of the definition of the direct sum. So we have this theorem proven. The consequence or corollary of this theorem is that if you have a n by n complex matrix with n distinct eigenvalues in C, then we automatically know that the matrix A is diagonalizable since the dimension condition 2 is satisfied. We don't have to worry about repeating eigenvalues. If all of them are distinct and add up to n, that means that A is diagonalizable. So diagonalizable matrices are almost like diagonal matrices. For example, from this identity A equals UD U inverse, we get that if you want to raise A to the kth power, that means writing UD U inverse k times, then these in between U inverse U's cancel out since we have these pairs together, and that's the identity matrix, and multiplication by the identity matrix doesn't change anything, so we can leave them out. Then what we have is these D matrices in between k times multiplied together, and then the U and U inverse on the two sides. So we end up with U D to the k U inverse. And since D is a diagonal matrix, the D to the k is just the diagonals raised to the kth power. So that this means it's much less work to do this multiplication than to do the kth power. For example, if k is 100, that would take a huge amount of work to multiply out a matrix, a full matrix, k by k times. Instead of that, taking the kth power, no matter how high it is, this power for a diagonal matrix is just the n diagonals raised to the kth power. Also, if we denote with these column vectors u1, un, the columns of u, and then u inverse, for example, if you write it as a column vector, which means these v's, v1, vn, are row vectors. So the u's are column vectors, size n by 1, and the v vectors are row vectors of size 1 by n. Then we can also write this a to the k equals u d to the k u inverse, writing out the u as a matrix of the column vectors. Then the d to the k is just the diagonal entries with the eigenvalues raised to the kth power. And then u inverse, the column vector of the v row vectors. Then the way we multiply, for example, starting with this multiplication of the diagonal matrix with the column vector, the way we multiply it, so the row multiplied by the column, only the first entry gets picked up because the other entries are 0 here in this row. So we get in the first entry lambda 1 to the k v1, and so on. So the last entry is just lambda n to the k vn. And then when we multiply this from the left with this U matrix written as a block vector, what we get is the sum of u1 lambda 1 to the k v1, and lambda 1 to the k is a scalar, so we can write it in front, and then we sum it up, lambda j to the k uj vj, as j goes from 1 to n. So this is another way to write this multiplication. We have also seen that a minus lambda I n equals to u times d minus lambda I n u inverse. That was in the proof of the previous theorem. And then that means that if lambda is not in the spectrum of A, if it's not an eigenvalue, then this diagonal matrix D minus lambda in has no zero diagonal entry. And if that's true, that there are no zero diagonal entries, that means it's invertible. We have seen this before. That theorem was actually for triangular matrices, but you can consider also diagonal matrix as a special triangular matrix. So then what we have is that A minus lambda I n to the inverse is U D minus lambda I n U inverse. And then the way we invert this product, we have to change the order. But once you change the order, U inverse go to the left-hand side and you have to invert it. The inverse of the inverse is U itself. Then in the middle we have the D minus lambda I n inverse, and on the right we get the inverse of U. And then we have this similar multiplication like before, except for the diagonal entries here. This is diagonal matrix, and the inverse of the diagonal matrix is just the reciprocal of the diagonal entries that are 1 over lambda j minus lambda. And then using this identity like before, we actually have to add these up when we multiply this with uj, vj. So inverting the matrix is also easier if we know the diagonalization of it. Later we will also work with matrix exponentials that can be defined and calculated the following way. So this comes from the Taylor expansion of the exponential function, but now we replace the variable x with a matrix. So we can define it as the sum as k goes from 1 to infinity, a to the k over k factorial, and then everything is defined here. The kth power of a matrix is defined. We can divide it with a scalar k, and we can add them up. Of course, the question is, how does it converge as we add up infinite sum? We will talk about it later. But the point here is that we have a formula for the kth power of a. That's u times d to the k u inverse if a is diagonalizable. And then it's a sum. Well, it's an infinite sum, but let's assume that we can also factor out u, constant matrix from an infinite sum. If we do that, then we get u on the left and u inverse on the right. And in the middle, we have this sum. And here we have the sum of d to the k diagonal matrices. But that one is just the kth power of the diagonal entries. So if we sum up this, just the diagonals, because everything else is 0, we end up with the sums of scalars, lambda 1 to the k over k factorial, and then lambda n to the k factorial added up. But this is then the definition of the, not the definition, but the Taylor expansion of the exponential function with exponent lambda 1. So we can write this as e to the lambda 1, e to the lambda n, multiplied with u from the left and u inverse from the right. So this is another way to work with the matrix exponentials. Section 4.7, an algorithm for diagonalizing matrices. The algorithm to diagonalize matrices is in the proof of when we said that 2 implies 1 in the previous theorem about diagonalizability. So what we need is, first of all, the geometric multiplicities, gammas, that are the dimension of the null space of a minus lambda i's, where these lambda j's are the eigenvalues. So we get the geometric multiplicities gamma j as j goes from 1 through k. And we need that these meet the constraint that gamma 1 through gamma k, when added together, gives you n. Then, so that was condition for the diagonalizability. And then the process, what we did in the proof of this theorem was that we obtained the basis for each of the spaces, null spaces, a minus lambda j. We put together the basis vectors into a matrix, uj, Then we put together these matrices into a larger n by n matrix U, that's U1, Uj. And then we also put together the eigenvalues into a diagonal matrix D, repeating each eigenvalue gamma j times. And then we get that A times U equals U times D. Let me mention that still you are not allowed to use determinants to calculate eigenvalues, and also for larger matrices we can't even do that. We have to do row reduction of A minus lambda I, and to see we have to check the condition on lambda so that this A minus lambda I matrix doesn't have full rank. It has to have a less than n rank so that the null space is not the trivial zero vector. For example, let's try to diagonalize this matrix A. It's a 3 by 3 matrix. So the way we solve this is that we write A minus lambda I with some lambda variable basically, and we reduce it. We start reducing it. So in order to make this 8 disappear using the first row, what we can do is add to row 2 minus 8 over 9 minus lambda row 1. So that this division by 9 minus lambda creates 1 here first. Multiplication with minus 8 creates a minus 8. Added to 8, that becomes 0. But then, of course, we have to do this for each entry in the row. So we get minus 12 times minus 8 is 96 over 9 minus lambda. Added to minus 11 minus lambda. And the same thing, 96 over 9 minus lambda is added to minus 8. And then we don't have to do anything in the third row because it's already 0 in this entry, the first column, 3, 1 entry. So then from this matrix we want to check, because this is now upper triangular matrix, we can check to see how this can have less than full rank, less than 3 pivots. But before we do that, we should make sure that this calculation here makes sense. The problem is that if lambda is 9, that this whole thing doesn't make sense. So we have to check what happens if lambda is 9. Maybe this is an eigenvalue, maybe this is not. If this is an eigenvalue, then we have an eigenvalue, and then we cannot do this operation, we have to do something else. But if this is not an eigenvalue, then everything is fine here. So to check that lambda equals 9 is not an eigenvalue, we calculate A minus lambda I with lambda 9. Then we get 9 minus 9, 0 here, minus 11 minus 9, minus 20, minus 3 minus 9, minus 12. So we have this matrix. To see what the rank of this matrix is, we can just switch row 1 with row 2, and then we get an upper triangular matrix with non-zero diagonal entries, which means it has rank 3. It has 3 pivots, and that means it has a full rank, so lambda equals 9 is not an eigenvalue, because the null space of this matrix is just the 0 vector, which means it's not an eigenvector. So we can return to this matrix and check to see that how it can have less than 3 pivots. If lambda equals minus 3, then we have minus 3 minus minus plus 3, that's 0. So that means that here we don't have a pivot. Maybe we have 2 or even less pivots. So lambda equals minus 3 is definitely an eigenvalue. We also have less than 3 pivots if this 2-2 entry is 0. Then we have 1 and 2 pivots. Well, depending on what this lambda is, maybe just 1 pivot or at most 2 pivots. So this minus 11 minus lambda plus 96 over 9 minus lambda equals 0. can be multiplied through with 9 minus lambda. We already know that lambda equals 9 is not an eigenvalue, so we don't have to worry about 0 denominator. If you multiply through with 9 minus lambda, you get minus 11 minus lambda times 9 minus lambda plus 96 equals 0. Then we can multiply this out to get lambda squared plus 9 minus 9 lambda plus 11, that's plus 2 lambda. And then minus 99 plus 96, that's minus 3. And once we expand this product and simplify it, then we can go back and now factor it to get lambda minus 1 times lambda plus 3 equals 0. So the possibilities for this product to be 0 if lambda equals 1 or if lambda equals minus 3 that we already actually had. So what we have is that the eigenvalues are lambda equals 1 and lambda equals minus 3. The order doesn't matter, but then later we have to synchronize it with the eigenvectors in the U matrix. So next we turn to the geometric multiplicities in the null spaces. We basically want to solve a minus lambda 1 I x equals 0 for x. So if we look at this a minus lambda 1 I, lambda 1 is 1. So we subtract 1 from the diagonal entries, then we get 8 minus 12 and minus 4. Then we can do a row reduction, so subtract from the second row the first row to get 0, 0, 4. Then we can add the second row to the third row to get 0 on the third row. And then we can also divide the second row with 1 and divide the first row with 4, for example, to get 2 minus 3 minus 3. So this is a reduced upper echelon form right now. Now we can augment this with the 0 right-hand side since we want to look for the null space. And then the second row says that x3 is 0. The first row says that 2x1 minus 3x2 minus 3x3 equals 0. So rearranging this and using x3 0, we get that x1 is 3 half x2. Then combining these together into a vector x1, x2, x3. x1 is 3 half x2, x2 is just x2, free variable, and x3 is 0. Then we can factor out x2 to get 3 half 1, 0, or we can even factor out 2 to get x2 over 2, 3, 2, 0, in order to get a basis vector for the null space with integer entries. So we have that the geometric multiplicity of lambda 1, this gamma 1, is 1 because we have one basis vector. And the dimension of a minus lambda 1I is 1. Also, then we have that this U1 first matrix is just this column vector in itself. So it's a 3 by 1 matrix. Then we go to the next eigenvalue, lambda 2, which was minus 3, and consider a minus lambda 2i x equals 0. So for that, again, we consider the matrix a minus lambda 2i, and we're going to do a row reduction to get upper echelon form. So we have to subtract minus 3, which means we have to add 3 to the diagonal entries of the original matrix. That means we get 12, adding 3, we get minus 8 and 0. Minus 8 and 0. We can divide the first row with 12 and the second row by 8. And then we see that by subtracting the first row from the second row, that becomes a 0 row. So we only have one equation to solve for the null space, and that says that x1 equals x2 plus x3. Collecting together this into vector parameter form, we get that x1 is x2 plus x3, x2 is free, x3 is free. Then we can separate x2s and get 1, 1, 0, and separate x3 and get 1, 0, 1. So now gamma 2, the geometric multiplicity of the eigenvalue lambda 2 equals minus 3 is 2, because we have two independent eigenvalue vectors that form a basis for the null space, and that means that the second U matrix is just the two vectors put together into a 3 by 2 matrix. So with this we have the diagonal matrix with the eigenvalues in the diagonal entries 1, minus 3, minus 3. We have to repeat this minus 3 because we have multiplicity, geometric multiplicity 2. And we have the U matrix put together with U1 and U2 as 3, 2, 0, 1, 1, 0, 1, 0, 1, 3 by 3 matrix. Next example, it's a 2 by 2 matrix now, M. And now we want to find a formula for the entries of m to the n, where n is a positive integer. And the solution is that we want to diagonalize this M matrix and then write m to the n is u d to the n u inverse. So for that we have to go through the diagonalization process, finding the eigenvalues and eigenvectors. It's a 2 by 2 matrix, so hopefully it's not going to take as much time as the previous example. We subtract lambdas from the diagonals to get 2 minus lambda minus 1 to 5 minus lambda. Then row 2 will be row 2 plus minus 2 over 2 minus lambda row 1, so that we get minus 2 here, and then added to 2 it cancels out. We also have to do the same thing with this entry, so we get minus 2 times minus 1, 2 over 2 minus lambda added to 5 minus lambda. We have to make sure that 2 minus lambda is not 0. That means we have to check what happens if lambda is 2. Then m minus 2I is 0, minus 1, 2, 3. And then switching row 2 with row 1, we get 2, 3, 0, minus 1, which has 2 pivots, and that means lambda equals 2 is not an eigenvalue. So otherwise then we can return to this matrix and say that lambda is an eigenvalue if and only if there are less than 2 pivots in this matrix, which means that this can happen only if this entry is 0. 5 minus lambda plus 2 over 2 minus lambda must be 0. We solve this for lambda. Again, we can multiply through with 2 minus lambda since we already know that this is not 0. Then we get 5 minus lambda times 2 minus lambda plus 2 equals 0. Multiply it out, lambda squared minus 7 lambda plus 12. And then factor again. But now we have just 0 on one side and the factory on the left. So once we have a factorization, we have a product, then we know that the only way this is 0 if one factor is 0, so lambda is 3 or lambda is 4. Then eigenvectors, that are the basis of the eigenspaces. So we look at m minus lambda 1i or m minus 3i in this case. And that's, we have to subtract 3 from the diagonals. We get minus 1 and 2. So it's minus 1, 2, 2. We can multiply the first row with 1, and we can also add 2 times the first row to the second row to get 1, 1, 0, 0. Then only the first row usable, and that says with respect to the null space that 1x1 plus 1x2 equals 0 if we augment it with the 0 right hand side. And from here we get x1 equals minus x2. Then putting it together into vector parameter form, we get that minus x2, x2, and factoring out x2, we get minus 1, 1. So we have one eigenvector. Then to get the other eigenvector, we consider m minus lambda 2, which is m minus 4i. Subtracting 4 from the diagonals, we get minus 2 and 1. So we get minus 2, minus 1, 2, 1. And then adding the first row to the second row, we get 0 row. Then multiplying with minus 1, we get 2, 1. So this is 2x1 plus x2 equals 0, or x2 is minus 2x1. Well, the reason I solve for x2 instead of x1 so that I don't get a fraction. It doesn't matter how we do this, it's very short anyway. So writing it this way, we get that the x vector, the eigenvector, can be written as x1 minus 2x1. Factoring out x1, we get 1 minus 2. So we have the two eigenvalues that we can put together into a big matrix, while it's only a 2 by 2 matrix. Minus 1, 1, and 1 minus 2, column by column. And then the corresponding diagonal matrix is the eigenvalues in the diagonal entries, which is 3 and 4. You have to make sure that the order is correct. So we have here the eigenvector corresponding to the first eigenvalue, and the second eigenvector corresponds to the second eigenvalue. Well, in this case, because we want to calculate u d to the n u inverse, we also need u inverse. So let me remind you how we calculated u inverse using the Gauss-Seidel method. We put together u and the identity matrix, and then we do a row reduction, but not just to get an upper echelon form, we want to get an identity matrix. And once we have that, the right-hand side is the inverse matrix. So that means that this M matrix is u d u inverse, and also the nth power of the N matrix is u d to the n u inverse. And for d to the n, we have that is just the nth power of the diagonal entries. Then we can multiply this from the left with this U matrix and from the right with its inverse. Doesn't matter which order you do, either from the left or from the right. You can start, I here started from the left to get minus 3 to the n, and make sure that you understand that minus is outside the power. And 1 times 0. Then we have minus 1, 0, 1, 4 to the n for the 1, 2 entry. Then we have 3 to the n times 1, and then minus 2, 0, that's not 0. And then 1 times 0, minus 2, 4 to the n is just minus 2, 4 to the n. Then we multiply it from the right with minus 2, minus 1, minus 1, minus 1. It's a short calculation. We get a formula which is not completely trivial, but the idea is that this is much, much better formula than trying to calculate the nth power by multiplying the original full M matrix n by n, or n times. Section 4.8, so these are short sections. Section 4.8 just says that not all matrices are diagonalizable. So in this theorem about diagonalizability, we have this condition that the geometric multiplicity should add up to n, and it's necessary and sufficient for diagonalizability. And unfortunately, sometimes this doesn't happen. We don't have enough linearly independent eigenvectors. For example, if you look at this 2 by 2 matrix, looks innocent enough. We have only eigenvalue lambda equals 2. It has multiplicity 2, but this, what you see here, is algebraic multiplicity. To get the geometric multiplicity gamma, we have to look at the null space of A minus lambda I, which is A minus 2i. So you have to subtract 2's from the diagonals. You get 0, 1, 0, 0. And that means that x2 is 0. That's the only thing that we get out of it. And that means x1 is arbitrary. So we have the null space of A minus 2i is just the span of the 1, 0 vector. And that means that its dimension is 1. So the geometric multiplicity is 1, although the algebraic multiplicity is 2. And because the geometric multiplicity is 1, which is less than 2, the dimension of the whole space, since it's a 2 by 2 matrix, we are working in the C2 space. Since the geometric multiplicity is less than the dimension of the space, that means the matrix is not diagonalizable. Larger matrices can be also constructed in a similar way. For example, This upper triangular matrix has also the same problem that the 2 is the only eigenvalue, but it's repeated 3 times. If you want to look at the geometric multiplicity, subtracting 2 from the diagonal entries, we get 0, 1, 0, 0, 0, 1, 0, 0, 0. And what this says is that x3 is 0, x2 is 0. And again, we have that x1 is the free variable, so it's 1, 0, 0, and it's span that creates the null space of A minus 2i. We have the same problem that the gamma, the geometric multiplicity of the null space, is 1, which is less than the dimension of the space, that is 3. So again, A is not diagonalizable. However, if we start taking the power of this, we did similar thing for the Jordan chain. So A minus 2i to the 2, if you multiply it out, you get 1 in the 1, 3, and 3, and 0 everywhere else. And then if you take the third power, you end up with the 0 matrix. And this now means that if you want to find the null space of this, the null space of this 0 matrix is the whole C3 space, since it doesn't matter what vector you choose. When you multiply with the 0 matrix, you get the 0 vector. So it's interesting that we are working in the 3-dimensional space, and although we have less than, the geometric multiplicity is less than the dimension, what we have is that if you take the third power of this A minus lambda I matrix, then the null space will give you the whole vector space. This is actually true in a more general setting when we have different eigenvalues, but maybe the geometric multiplicities don't add up to n. So that's the next theorem. If we have a n by n complex matrix, and A has exactly k distinct eigenvalues, lambda 1 through lambda k, then what we have is that Cn equals to the direct sums of the null spaces of A minus lambda 1i to the n, plus the null space of A minus lambda ki to the n. The proof of this theorem will be discussed later, and also its applications or implications will be considered in the next section.